Okay, in this video we're going to look at Hooke's law and deforming materials. For a couple of videos we'll look at material physics and the kind of questions and kind of ideas that you need to have. Right, so let's start off with the first two words you need to be aware of when it comes to materials. Is that materials can undergo compressive forces, that's where you compress something, and then where you can undergo tensile forces, with which you can pull them apart. So in terms of the types of springs you can get springs that are compressive springs, ones that when you push them together they ping outwards when the force is released. A good example of that is just, standard suspension spring. And then you've got the springs that you'll be using in the lab, the tensile springs, which start from a small position, and as you expand them, when you release that force, then they ping back together and come together. So you've got the two different forces, compression and tensile. So those are those two forces, and what you need to be aware of is that springs nicely model what happens in most materials. Now that's because of the atomic interactions. It's not actually that simple, but it models it quite nicely, and it models our observations very well. And we can use the same principles to apply them to materials in general. You'll see that happening in the next few videos. So let's jump straight into Hooke's law. So Hooke's law, a standard experiment to look at Hooke's law would be to have a spring with a mass attached on the end. And what you would normally do is you would add a mass, measure the extension, add another mass, measure the extension, add another mass, measure the extension, and essentially what you're going to end up with there is loads of forces that you've applied to that based on G. So you work force out by mg based on the mass that you placed on it, and you get the extension. And we plot a nice graph of force against extension. Now, one thing I will say about extension is the extension is not the total length. The extension is how far it's gone from its original size. So when you're doing this, you'll want to measure the spring when it's got no load placed upon it, and then you'll measure the distance from a point on the spring to the new point on the spring, and that distance is the extension. Nice way of thinking about this, it's the original length of it's the new length of the spring minus the original length will give you the extension. Okay? So the new length of the spring minus the original length will give you the extension. That's very, very important, and it's the original length from the very beginning, not from the reading beforehand. Okay, that's a very important point as well for your notes. So new length minus original length gives you the extension. And what you'd end up with is a very, very nice straight line, just like that. And we'd expect that from a spring, and we'll expect that in your results in your tests that you'll do in the next lesson. And like I said, this is what's going to give rise to Hooke's law, because as with any straight line graph, we normally look at the gradient, because that represents the rate in which the increase occurs. So we do force over the extension. So to work out the gradient here, you would do force over extension will give you a gradient of what we call K. Now that K is what we call a force constant. Now that force constant is really, really important because it is an intrinsic property of that material at this time. So what we have here is a quantity that is a constant for this material or spring as you add a load to it. Now what we have here is we can suggest a unit for the force constant, because we've done force over extension. Force is in newtons, extension is in meters, so we've got a unit of Newton per meter. Okay, newtons per metre this time. So watch out for that unit. So that's your force constant there. And it's really quite useful because this is Hooke's law in simplicity. And it's stating that the force and the extension are directly proportional to one another. So that would be written like force is directly proportional to the extension, where the constant, any force, is equal to a constant times by the extension that is exerted by that force. So that's a brief overview of Hooke's law, and it's about the proportionality between extension and forces that you place. Bear in mind, this also applies to compression. So if I was to compress a material, I could measure how much it shrunk by, and it would have a same constant of proportionality as the expansion, okay? So we'd expect that to be the case, because compression and tensile forces, they're acting in the same plane, but just in different directions. Okay, so that's just an introduction to Hooke's law, and in the next video we'll look at what happens when we have multiple springs.